Good afternoon, everyone. I am Jim from the Software Languages Lab at the VUB in Brussels, and today I'll be talking about a versatile programming framework for eventually consistent systems. First off, I'm sure most of you all know what eventual consistency is, but let me give a quick reminder. Eventual consistency is a consistency model which is used in distributed computing to achieve high availability, and guarantees that, informally, that if no new updates are made to an item, eventually all accesses to that item will return the last updated value. So temporarily there may be inconsistencies in the system, but eventually things will become consistent. An example of something that is eventually consistent are CRDTs, or conflict-free replicated data types. And we all know CRTs, they're a hot topic in this workshop, but let me give a quick reminder. CRTs are a family of replicated data structures where replicas can be updated and independently and concurrently. They can diverge, but if all updates stop, they eventually converge to the same state. And this is quite powerful. There are really nice things you can do with it, but sadly it's not always easy to use them in a programming environment. And this is because while CRTs are intended for integration in programming language, a lot of research and work on them focuses more on formalisms and design than on practical issues, which make that they do not translate well into actual frameworks or abstractions. And this leaves many questions over to the end user and developers, such as how they manage distribution, perform memory management, or handle security. And as part of my PhD, I am looking into solving some of these problems. But in order to do that, I need a programming environment where I can program and experiment and basically to test and develop solutions for CRDT implementations. So I started exploring ways to have such an environment, and basically I had some requirements. Mainly, first of all, my code and my tests have to be able to run on multiple platforms, not only my computer, but also my mobile phone or embedded hardware with low resources. Additionally, I don't want to be fixated to a certain networking approach, so I don't want to be limited to a certain topology, so I had to have an agnostic network approach. Furthermore, the framework has to be extensible. Basically, I should be able to, with reflection, be able to add hooks into the replication process of a CRT, etc. So this all led to an artifact of my research which I named Flec. And Flec basically allows you to create and build applications for CRDTs for various languages. So it does so by targeting actually WebAssembly. And for those who don't know, WebAssembly is an open standard that basically defines some portable binary code. VMs exist for several platforms such as your web browser, Node.js, embedded hardware. And the nice thing about it is that a lot of compilers can target WebAssembly. So basically many languages can be transpiled or compiled to WebAssembly. And I took advantage of this to build a framework for building CRTs and other eventual consistent data structures, which can be used by different languages that can compile to WebAssembly. To add support for a certain language, all you would need to do in this framework is basically add a translation layer, a language provider that takes a primitive value in one language and converts it to a primitive in WebAssembly. And this allows you for a very nice networking approach. The core to Flec is basically a module we call TSAT, which is actually a mini framework on its own, and it implements an ambient-oriented programming environment. And in such an ambient-oriented environment, developers are provided with an actor-based programming model where actors can communicate and coordinate over dynamic networks. And to this end, TSAT brings support for ambient acquaintance management, so that is basically discovering other actors on the network or objects published on the network in a network agnostic approach. And has support for non-blocking message passing between actors, failure handling through message buffering, leasing, and feature-like synchronization constructs. On the right side, you can see here some code, which is basically a TSAT program. And basically what I have here is a class ping-pong, which implements a ping and a get counter message. And I export this class on the network using do export. And once this is done, other devices running Flec can discover such a class such an object, and they will obtain a for reference to that object, and then they can send messages to the remote object, and etc. And this, of course, here we have all nice failure handling, networking, all behind the scenes. And this is all handled by TSAT. We also have implemented several modules to implement and work with CRDTs. So basically, we have a base CRT layer where we can implement state-based or operation-based CRTs. We have a layer that allows us to create operation-based CRTs that rely on reliable causal broadcasting for causal ordering of operations. And we implemented a layer that provides users with PO log CRDTs. On the right side, we see some other code here, and basically I have twice the same code, but just in Lua and one in TypeScript. And basically, what we're doing here is we're creating a counter CRDT, and in Flec, when you create a CRDT, what you will always do is you will have to give a certain tag name to it, and this tag name is used to identify the replica, well, the CRDT on the network. And every time you instantiate a CRDT with that tag, it will automatically be linked with all other CRDTs using that tag, all other replicas. So basically what we do here is we set an update handler, which will print every time the CRDT is updated. But I'll give now a more complex example. So we have a M5 stick platform, which is an embedded platform that relies on an ESP32 IoT platform. And basically this platform has a 240 MHz CPU, 520 kilobytes of SRAM, 4 megabytes of flash, and it has Wi-Fi and Bluetooth, and in this case we also have a small display. And we will be running Flec on this in VM, and it has also a graphical interface for on the small display written in C++. I'll not show the C++ code, but the Flec code is actually really simple. So we import our Flec definitions, and then we create an adwin set, which we name color set. We set our update handler to update display. Update display will call some callbacks from the C++ rel to update the screen. Then we set a new replica handler, which just basically every time we discover a new device, we'll blink a LED. And basically when C++ graphical user interface performs a local update, it will send also an on update message, where we will then basically mutate our set. So let's look at the demo. So here I have 3 devices, and I'll turn them on, and every time they discover each other, basically what happens is they'll blink a LED showing that they discover each other. But I will be able to add colors, specific colors, to a set. So on the bottom device I'll add a color, I'll add yellow. You can see as soon as I add the item to the set, it is propagated to all other devices. Of course I can update the other devices, so I'll add blue, which is propagated immediately to the devices around it. This is all done over Wi-Fi, of course. What is also interesting is that I can disable the devices now. So now I'll just be able to top 2 devices, and this is nice because then I can test concurrent updates in the framework. And so if I add an item, so I'll add a gray item to the bottom device, you can see that, or purple, you can see that it's not propagated to the above 2 disconnected devices. Of course, I can still update the disconnected devices themselves, so I'll add green, and you can see it's not they are not propagated to the other device either. I'll remove an item, not propagated either, but as soon as we reconnect the device, so I'll reconnect the first one, it will be immediately propagated to the device below. And now you can see that all nodes are synchronized. Of course the order is slightly different, and this is because we're using a set. It's not really significant, but it's quite neat. The implementation details of the adwin sets are actually quite simple as well. Basically we extend our PaPoC interface, and we will have to implement several implementations. So is redundant by operation, is redundant by log, set entry stable, and remove entry. And these allow us, using these methods, we can implement the semantics of our CRT in a PaPoC based way, and we'll automatically get causal stability. We also have a toList operation, which I don't have all the code here for brevity's sake, but basically it gets the log and it takes the local compacted state and it will combine them to get the current state of the CRDT. And then we have basically add, remove, and clear operations, which you can use to mutate the set, and they will basically use the underlying perform op method to basically add an item to the log, and which will be automatically propagated as well. So to recap, to conclude, Flec is a versatile programming framework for eventually consistent systems. It allows you to experiment with eventually consistent data types, and it's quite flexible, which is very nice for my research. And for future work, I'll be looking into modular approaches for memory management, because I'm running this on low on embedded devices with low memory. And I'll also look into trust management, so how can I authorize certain operations for certain users. And finally, of course, I will also add extra languages to Flec itself. Thank you for listening, and if you have any questions, please go ahead.